windshield.
All right.
All right.
So is that on the island stretch of 528? Was that here? Bob?
What's that?
It was on 528, is that on
528,
on the
yeah.
island?
No, it was over. I don't know. Remember now which way they were going, but they were supposed to be somewhere else and they were cruising International Drive at night.
I'll say probably out there like Christmas.
Yeah, probably on the mainland. Oh, boy. They don't want to be an international drive.
Almost like that, you wish you were sold.
Yeah, well,
How old was
it does wake you up.
How old was she at the time? Just interested.
Still in high school, like 17.
Okay. Oh, so.
Okay, what?
You raised a hellraiser.
Oh, yeah.
Yeah.
She's a school teacher now.
That'll teach her.
Amplifiers, okay. We're going to talk about classes of operation, a little bit about vacuum tubes, distortion, spurs, microwaves, and switching amplifiers.
What's a switching amplifier?
A class D through
Class
T.
D, yeah.
Okay. So this little chart shows for different classes of amplifiers, the conduction angle, which is what percentage of the input waveform the transistor in the amplifier is actually powered on, okay, and conducting current or power. So a class A is the most linear of the amplifiers. It's also the least efficient because the transistors are always on. They're in some state of that waveform.
With the least amount of distortion.
The least amount of distortion, the most linear. Not necessarily perfectly linear, but it's the most linear. Because the devices themselves have some nonlinearities. Then they came out with a class B, okay, which normally is a push-pull configuration. So you've got two transistors set up, so one of them amplifies the positive part of the input waveform. The other one amplifies the negative portion. Now, because one's on and then the other one comes on, if you remember about the p-in junction thresholds, the 0.7 or 0.3 volts, you've got some offset there. So there's what they call crossover distortion, okay, in that midband. So one of the things they did to get rid of that is come up with the class AB amplifier, where they changed the bias a little bit to get rid of that offset, and it conducts for a portion of the opposite cycle. So if you can see in the diagram there, on the negative cycle, it's actually conducting down to like the 0.7 volts. Then, and it's not quite as efficient, although it's close to a B. And a B is more efficient than an A. And that curve is basically the efficiency curve. A class C is of the analog is the most efficient, but it only amplifies a portion of the waveform. Okay. So its conduction angle is 90% or less. And then you have a class D, which is essentially a digital amplifier, where you convert the input signal into a pulse width modulated waveform. So the higher the input voltage, the wider the pulse. And you can switch very large amounts of current doing that, because the switching transistors are either off or on. So there's very little power dissipated in the transistor. So it makes them very efficient. But you have to then run that through a low pass filter to get rid of all those high frequency components to make it to smooth it back into the approximate input waveform, but there's still a lot of distortion. So you can't really use that type of amplifier for phone or single sideband. You could probably use it for FM. So for a Class A, this is kind of a typical simple Class A transistor amplifier. And you select the operating point when there's no signal to be about midway on the load line. And that load line is a function of your load resistor, that RL in the circuit, where when it crosses the vertical axis, which is the voltage axis, that's when it's at cutoff. So there's no current. You got your supply voltage, basically VCC, across the transistor. The other end of it is on the horizontal axis, or the current axis, and that's when it's in full conduction. So it looks like a short circuit. So you operate on that line, and assuming the transistor's linear, then the output is going to look just like the input, with some gain depending on the gain in the circuit, the relative resistance of RL and RE. And you bias it with that R1, R2 network to set the bias voltage on the gate. So you calculate that so that you can put the operating point there in the middle. And part of that bias is the emitter resistor, okay, which is going to generate what we call self-bias. And the capacitor around there is going to smooth that out so it looks like a DC voltage source. That's the opposite polarity of the bias circuit over on the left-hand side. The key is that you operate it halfway between saturation and cutoff. So where on the load line of a Class A common emitter amplifier would bias normally be set?
You just said that.
Yeah, the lack of sound like.
I was seeing it if you paid attention.
Oh. Can I leave now then? Take it?
Okay, Class B or push-pull. Okay, we got two transistors. And like I said, one is set up to amplify the positive portion of the waveform, the other one the negative. It operates on that load line, except at the bottom. So it goes from saturation up. So it's only conducting for, each transistor is conducting for half of the cycle. The one advantage of doing that is it gets rid of the even order harmonics. So, which of the following reduces even order harmonics?
Push-pull.
The Class B is kind of hybrid. Essentially all they're doing is changing that bias network so that it conducts on part of the opposite cycle so that you don't have that crossover distortion. And that causes it to lose some efficiency compared to a B. So what portion of the signal cycle does each active element in a push-pull Class AB conduct?
So is the distortion due to the difficulty of the circuit going from cutoff to saturation? Because it drops to zero and then you have to restart. So is that what causes the distortion? It's it's interrupted. The
Well-
circuit is kind of interrupted.
For the B, okay, the signal comes in, so it has to get up to the bias voltage in order to conduct. And the negative cycle has to do, so you've got this little band in there where it's not conducting. So you're getting
So you're missing.
most of this cycle and most of that cycle, but right at the crossover, you've got a basically.
Until it starts operating efficiently, you're losing that amplification.
And that's what all they're doing is changing the bias with those diodes is
So
one way to do it.
So
Okay,
it's
so that it conducts,
during the crossover.
well, you don't see the crossover. Basically, get rid of the crossover. Okay, a class C, like I said, only conducts for a portion of the waveform, and it requires having a tuned circuit to actually make it work. So if you use this in the output stage of a transmitter where it wasn't going to be phone, okay, that portion of the signal coming in that gets amplified basically causes that resonant circuit to resonate. So, it's a narrow frequency amplifier. It's not broadband. It can only operate within the bandwidth of that tuned circuit. And it just keeps the tuned circuit going, and that's where you get your amplification. And it's conducting for less than 180 degrees. Now we got your digital or class D, where you take the input and sample it. In this case, you're showing using a triangle generator. The scale is off on these because you do it at a much higher frequency than the frequency of that input signal. And it creates a varying pulse width for every one of those samples. Every triangle is going to give you a different sample. So where that in the comparator, where that equals the input signal at that point in time will determine how wide that pulse is. And all you do is filter them after you've gone through some switches so that you can operate at higher voltages and currents. And then you just filter it back out. You normally see these in audio amplifiers because you can't do this kind of circuit at real high frequencies. So what is a Class D amplifier? So uses switching technology. Why are they more efficient than linear amplifiers?
They operate at or near saturation and cut off most of the time.
Right. It's either off or on. And where you get power dissipation in the transistor is when it's somewhere in between. Which of the following components from the output of a Class D form the output of a Class D amplifier circuit? Read better here.
Low pass filter.
Yep. A low pass filter or an integrator. Okay, for power amplifiers, quality is important. If they're not designed right, you can get a lot of harmonics. Things like the power amplifier in the Baofeng handheld, which supposedly has been fixed, but they put out a lot of harmonics initially. You can install parasitic suppressors. And what do we call those? Ferrite beads, right? Or you can neutralize the stage by bringing some negative feedback. In other words, you you take the output signal and shift it 180 degrees, feed it back into the input so it cancels part of it, and it will help offset any oscillations. Because remember, how you make an oscillator is you build an amplifier and poorly, and it gets some positive feedback. So this is a way to offset any of the positive feedback by countering it with some negative feedback. And it might keep it from oscillating. So what can be done to prevent unwanted oscillations in an RF power amplifier?
Let's see.
So when you feed back the negative, you're calling that neutralizing?
Yeah. You're neutralizing the oscillations from the positive feedback. You're canceling them out. So how can it be neutralized?
180 degrees out of phase.
Fading out of this portion.
Let's see. Okay, so basically this is saying you normally would use a class A or a class AB linear amplifier. If it's anything that requires linearity on the waveform, which you would do for phone or single sideband, which is phone.
Class A is not efficient at all. I mean,
It's not efficient, but it's linear. It's the most linear. So it's everything in life is a trade-off.
yeah.
So if you want to have more efficiency, then you're going to settle for distortion in the signal.
Hmm.
So they don't recommend using class C for things like single sideband or phone because of the excessive distortion, and that distortion creates excessive bandwidth because you've got a lot of spurs out there. So which of the following is a likely result when a class C amplifier is used to amplify a single sideband phone signal?
Distortion D.
Distortion, excessive bandwidth.
Yep.
So where would a class C amplifier work well? Doesn't ask that question, but
Yeah, that's a good question.
they do use class C amplifiers, but what would be the application of class C amplifier?
Would it be CW?
It's even,
Yeah, CW wouldn't care much about the
we
nonlinearity.
talk about modulation being amplitude oriented, which sideband and AMR, but CW is just a fixed carrier.
Ambulance siren.
There's no,
Yeah.
there's no modulation of any kind on CW.
FM shouldn't be affected.
Constant amplitude, they're just changing frequency.
Some of the digital modes, perhaps,
Which are also
like
fixed amplitude.
phase modulation or PSK should work.
Exactly. So it doesn't really get into that, we just said there is, it's not like class C amplifiers are never used, there is a place for it to use.
When I look at how far FT8 has come, or any digital mode, as far as signal to noise ratio and how well they perform, I'm surprised they haven't converted all of our transmitters over to digital. Even on voice.
Well, most of the new ones can do both or all the above.
But like FT8's just using your sound card in your computer to make a sound in a single sideband circuit, right?
Yeah, mostly
just
you
putting
use
in-
single sideband, upper
it's just
sideband
putting
to do
eight
digital
tones
modes.
into your single sideband
But this doesn't do single sideband yet, and it does FT8.
That doesn't make sense, does it?
Well, nothing requires you to use phone to do digital.
Well, no.
It does have a sound card in it, though.
All of us like to talk.
That's true.
Mhm.
Some more than others.
Some more than others.
Okay, so,
I have a question.
okay,
Yeah, in other words, I'm trying to think, if you're designing a system and you're gonna get the, for example, like let's say I got a system that's transmitting music in the ear, and so I can have distortion that the ear cannot detect. So I might get away with some of these different amplifiers. But let's say I'm like a cell tower. I'm sitting zeros and ones, and I can't afford to knock out a one or zero. You know what I mean? Other words, how do I pick these amplifiers based on the type of output I'm expecting and how much distortion I can expect in the system? Like I say, some things I may not be able to detect it, right? Like an audio amplifier, maybe a class B, a class C. I won't hear it in the ear, right?
well, yeah, it definitely depends on the person. In fact, a lot of the musicians, from what I understand, not being one, prefer old tube type amplifiers because they sound better, because they like the distortion that's produced in them, as opposed to a transistor, which they describe as like clinical, or because it doesn't have the same distortion. So it depends on what you want. A lot of hi-fi people would go for the tube amp with distortion because they like the sound. But then the tube amps nowadays are probably not cheap. Like the old Macintoshes with
Yeah.
those tubes.
But if I'm
Mark
but
or something like that, yeah.
if I'm transmitting digital data, high speed digital data, I got to be able to detect that one and zero. So I can't have a certain amount of distortion. And I guess they got this stuff called robustness and all these other techniques where distortion is tolerated as long as I can recover a one or zero, right?
Right. Well, the digital stuff's fairly tolerant because you got a large signal to noise ratio normally. In other words, you'll have a big difference between a one and a zero, however the symbol is done, whether it's phase or frequency.
Mhm.
But enough of a shift difference that it's fairly tolerant of noise and stuff. Did that answer your question?
Yes.
Okay.
Mhm.
Okay, so we still have vacuum tube amplifiers around. Linear amplifiers for amateur radios are probably 50-50 now. When you look at them, half of them are still tubes. I think the 1500-watt ones tend to be tubes more than I don't think I've seen that many transistors 1500 watts. They're usually smaller, like 600, 500.
Do they, in the modern amps, do they go from different classes depending on the modes?
Yes, in some of them, they have a mode switch.
You can capitalize on the class of.
That's on the general test about the mode switch on the power amplifier.
And it changes
It changes the operation of the amplifier depending on whether you're in FM or single sideband. At least that's what it says. I've never had one, so I can't say from experience how they work. You got one?
No,
Anybody got a power amp?
I have an amp, but mode doesn't.
Okay.
I have some that I've never turned off.
Okay.
No, I just don't have a mode switch at all. It's all the same.
So they'll normally in the tube type, the output circuit will have a pi network as the output filter and also as a matching network. So in order to tune it up, and it's my understanding, you kind of have to tune them for every band. I'm not sure if it changes with the mode, but the Pi network is a shunt capacitor on the input, a shunt capacitor on the output, and a series inductor in between, making it look like a pi symbol. So in order to tune it, you tune the input capacitor or the tuning capacitor for the minimum plate current, because they'll have a meter on the front so that you can see the plate current.
So it dips and
Right, you minimize that, and then you do the output or loading capacitor for maximum. And then you go back and you do the input one, and you just play with those until,
that's not just linear amplifiers. My old Drake was the same way.
Yeah, well,
You know,
they haven't changed.
anything with tubes.
Right, that's the way it works. So you play the little game of lowering one and maximizing the other. So when you get to the point where you can't get the plate current any lower on the tuning, and you can't get it any higher on the other one, you're tuned. I guess that would mean they're both the same, right? Same plate current, I would assume. Well, it should be the
I
same.
remember, maximizing it and then dipping.
Right. There's only 1 meter. We didn't have 2.
Right.
It was only 1.
But there was a switch.
Yeah.
You'd switch to
Yeah.
look for it to dip. And then back to full operate.
Did the switch put it in lower power?
No.
It just monitored something.
Okay, which of the following describes how the loading and tuning capacitors are to be adjusted when tuning a vacuum tube RF power amplifier that employs a Pi network output circuit? Another mouthful one.
A lot of words.
A lot of words. Maybe on the next one they'll shorten that. Because that's what they did on the general when they changed it. They went and reworded a lot of the questions so they weren't as wordy. Okay. Back to a common emitter amplifier. This is probably the most common form. It's called common emitter because the emitter is connected to ground. It may be through that self-bias resistor R3, or it could be directly to ground. The purpose of R3 and C3 is to provide self-bias as part of the bias circuit to stabilize the circuit due to temperature variations and things versus the R1, R2 bias on the gate, or the base, excuse me. So basically, that's a typical common emitter. And we have some questions. So what type of circuit is that?
Common emitter.
A common emitter.
These are really easy when you ask us like within that
Just
very
told us.
same minute.
Well, see, it reinforces the
Yes,
answer.
yeah.
What's the purpose of R1 and R2 in the circuit?
Self-bias.
No, R3 is self-bias.
No, one or two are.
Voltage divider bias. Voltage divider bias would be your normal bias. You may or may not have the R3, but in a more sophisticated circuit, you would normally have R3. And in a lot of cases, and I can't exactly remember how to do it when we learned it, actually R1 would be coming from the collector side to also compensate for variations in the circuit. and made it much more complicated to figure out how to bias it. But that was a long time ago.
And another question, the bias,
Okay.
the bias determines when that transmitter is on, right? When current is flowing from the,
Correct.
from the
You have-
collection.
Yes, you have to bias it so that the bias voltage is greater than the threshold of the PN junction, which would be approximately 0.7 volts if it was silicon. So you adjust that somewhere above the 0.7 volts in order to get the base current that you want. So you have to figure out the proper base current in order to get the output current in the middle of the load line. Does that make sense?
Yes.
Because remember that the transistor is going to have a gain of maybe 50 to 100. So for every microamp going into the base, you've got 50 or 100 times that amount of current potentially flowing from the collector to the emitter. So if you look in the data sheets for transistors, and I guess they still show them that way, they'll usually show a bunch of lines for different values of base current and what the collector current is for that. So when you draw the load line through there, you pick the point you want and figure out the proper amount of bias for it.
Wait a minute, the bias, so the bias, oh, excuse me. The bias is determining the gain.
No, it determines the base current.
Okay.
In other words, the operating point with no signal.
Okay.
Some formula on the resistive value of the collector resistor
Right.
over, I don't remember if it was the R2 or if it was.
Yeah, I can't remember either, but it,
That determines the gain. What's
Right.
interesting in a circuit like this with no input, no input, the voltage on the base is just the ratio of R1 to R2 connected to DC. So it's
approximately,
right.
because there is a little bit of current.
Yeah.
But it's,
Well, so when you first apply voltage, essentially, when you can analyze these, because like at cutoff, the transistor is open, so there's no current flowing through R3, and you're looking at the base to emitter voltage for the bias. So with no input, there is more or less a fixed voltage on the base. It's just that the value of the resistors when you apply power,
Right.
what really happens. So where do you bias it? It could be it's somewhere between cutoff and saturation, right? So
Right.
if
if you had it set up for
resistors-
say 10 milliamps
Yeah.
total,
Yeah.
depending on your unknown load resistor, then you'd want to bias it like 5 milliamps. So whatever the base current is to provide 5 milliamps on the collector emitter.
So then the transistor is conducting to some work degree,
Right.
wherever you chose that, so you do have a voltage across R3, you have a divided voltage
Right.
in between R1 and R2,
So in
allows
that,
that to be biased on or off, and somewhere in between, so there's
right. In fact,
variations of conduction, in the transistor.
So you're just selecting when you want it to operate.
Yeah, it may not be just an on and off scenario. I mean,
Right.
cut off,
if it was a
saturation.
switch, then you have the bias
Yeah.
set, so it's either at saturation or cutoff, and then your input signal will go to the opposite state. So you either one or the other.
Yeah, so with no input, whatever that voltage is between R1 and R2 set on the base, notionally, then changes up or down with that. If you have a varying input, higher voltage is less, so it conducts more, conducts less as compared to the minimum voltage.
But unless R1 and R2 are very high resistance values,
So you're selecting the midpoint between.
right,
If you wanted to,
Right.
a variation of conduction that follows the input signal, you have to bias that somewhere in between cutoff and saturation. If you did it right in midpoint, which would be kind of called a class A linear amplifier, depending on the
well, yeah, and that's
your input.
that's what this one is basically set up for, is
Yeah.
a class A.
So you probably. try to bias
Assuming
it.
that R1 and R2 are
Yeah, the
biasing it in the
efficiency of
middle,
both the positive and negative
Right.
side.
right?
So you're varying the,
Favor one more than the other, because your bias was wrong.
Well, true, but sometimes depending on the characteristics, because the transistor won't be perfectly linear. Okay, so you may shift the operating point one direction or the other to keep it in the linear range, and you also may restrict it. Because if you operated it from saturation to cutoff, you're obviously going to have distortion on the cutoff and saturation ends. Okay, so you want to keep it in the middle, and a section of the operating point that's as linear as you can get it. I mean, it won't be perfect because they're real devices. Okay. Oh, skipped ahead. R3. Who knows the answer to R3? Called self-bias. Another common one you'll see is the emitter follower. And in this circuit, it has a gain of 1. But its basic purpose is like a buffer. It has a relatively high input impedance and a low output impedance. The output impedance is going to be determined by that RE resistor and the transistor itself. So you use that to isolate things like an oscillator circuit that you don't want to load and change the frequency. So you put something like this in between so that you can drive with more power and you don't need to amplify it. So that's all I can say about them, is they're very common.
What would be an application?
Like I said, to isolate a oscillator circuit
Oh,
from
an amateur radio, what would that be used?
to isolate your VFO from your
Okay,
mixer.
that's, okay, that would be,
Because the mixer is not going to be a high impedance depending on the type of mixer. So if you had that circuit in between, then you could drive the diode mixer easily because it's going to be a low impedance. So which of the following describes an emitter follower or common collector? Actually, let's see. Why do they call it common collector? Because the collector is essentially, well, it's not ground, but it's common to all the other circuits, to the positive power supply. So if you have several of these, their collectors are all connected together because of the power supply. There's no load resistor. Just how they came up with the name. So which of the following describes an emitter follower? With the low impedance output. And it's called a voltage follower because it's all it does. No gain. Just I guess you could call it a current amplifier. Okay, another problem with designing amplifiers besides the harmonics and stuff is thermal runaway, because as transistors heat up, you get more excited electrons and you get more current flow called leakage current. So it's kind of a vicious cycle. As the leakage current increases, it creates more heat. And the more heat you have, the more leakage current you have, and it gets to a point where it just goes unstable and increases until it doesn't work anymore. And you let the smoke out. So one of the ways in you design the circuit is to put that resistor in with the emitter. So it will limit the amount of current increase and help stabilize it. So there's several reasons for those emitter resistors. So what's one way to prevent thermal runaway in a bipolar transistor amplifier? I don't think this happens with FETs, but I'm not sure. I don't think it does. Because the effect there is the leakage current from the base to emitter, and that's why the emitter resistor helps limit it. So as that base emitter current due to heating increases, then it increases the collector emitter current, and that's more heat, you know.
Well, transistor is a current amplifier.
Right.
But FET is not, it's a voltage amplifier.
It's a voltage controlled current amplifier.
Mhm.
A slight difference. Nonlinear amplification. So if you have these external signals that somehow get in with your power amplifier, you can have what's called intermodulation distortion or products, and you get the nonlinear mixing of those signals, and they produce a lot of harmonics or spurs. The ones that you care about the most are the odd order or the third harmonic, because it turns out that even though the third harmonic is 3 times the frequency, the products of it, in one case, one of the products will be adjacent to your actual carrier frequency. So it's hard to filter them out because of the fact that they're within the pass, basically the pass band. So this little chart, which you have to look at carefully, shows that where F1 and F2 are the 2 signals coming in that are relatively close together. So when you have some intermodulation, you produce the second order and third order products. And if you look at the second order, okay, it's going to be on the high side, twice F1 or twice F2, pure second orders, or the sum of F1 and F2. On the negative side of it, okay, you've got one at F2 minus F1. Now they're pretty far away. If you look at the third order, okay, up here on the right, we've got, 3 times F1 and 3 times F2, pure third order harmonics. And then we've got sums, which turns out to be twice F1 plus F2, or twice F2 plus F1. They're still high frequency. But you also get twice F1 minus F2 and twice F2 minus F1, which are the same distance between F1 and F2 is how far they are from those 2 carrier frequencies. So they're very hard to get rid of, which is why you try not to generate the third order harmonics. The second order are easy to filter out. And if you use the push-pull stage, it tends to minimize the second order anyway. Is that clear as mud?
I just recently saw, on FT8, I saw, I guess it would be what, third order? Sitting right next to their signal. It was upper sideband on the lower side, there was a harmonic where you could tune in on that and read their signal on their harmonic. Because I thought it was more than one person.
How did it show up?
It
On the
was
waterfall or what?
On the waterfall. It was plain as day with two stations nearby.
He was your next door neighbor, right?
Well, they're in the same city, so they had to have been running an amp.
Oh, yeah.
But I mean, it was sitting there like, who are all these people? Well, it was the harmonics of those that were operating.
I've never seen it, but supposedly
I've never seen that
when you get
before.
the overmodulation and the distortions, it says in the textbook that you'll see lines along the side of the waveform in the waterfall. I've never seen them myself. Have you?
Well, that's what I was seeing yesterday as I was
Actual like vertical lines
a
along.
separate signal. It looked like another transmitting station, but it was their harmonic. And I tuned in on that harmonic and it was perfectly intelligible.
Yeah.
Before it was distorted, right? Was there any
No,
distortion?
no,
Not really.
no,
So you decoded it.
I decoded it. Yeah, it was, I've never seen that before.
It wasn't out of Mexico, was it? Because they run at least 1,500 watts.
It was 6
And,
meters.
and the bandwidth is about that wide.
And it'd be very red display.
Yeah.
What's the effect of intermodulation products in a linear power amplifier?
Spurious signals.
Yeah. Why are the odd order rather than the even order intermodulation distortion products of concern?
They're harder to. Can you say something harder?
Yeah, why are they harder?
Closer frequency
Right.
to the desired signal.
Okay, back to a tube, a grounded grid. Says they're easy to build, very stable. I guess there's a bipolar equivalent, which would be a grounded base. It's probably the typical output in most of the tube type stages. And it's set up so it does basically a 50 ohm output impedance, which makes it convenient. There's the typical circuit for one, where you've got a tuned circuit in the cathode in this, as well as in the plate or output circuit. So what's a characteristic of a grounded grid amplifier?
Oh, important case.
Okay. Any amplifier questions? Did I read that word? I'm good.